The second video in this playlist addresses the Universal Asynchronous Receiver and Transmitter, or UART, topic. The expected learning outcomes are that you shall be able to explain how a UART works. You shall also be able to describe the organization of a serial communications RS-232 frame, to describe the ASMV chart for a UART receiver, and to explain how to design it in VHDL. To start with, we ask what is a universal asynchronous receiver and transmitter. Well, it is simply a communications interface that includes one serializer, that is to say it converts from parallel to serial, and this is the transmit letter in the word, and also a deserializer, that is to say a block that converts from serial to parallel, and that will correspond to the receiving function of the UART. So the general block diagram for a UART, or the general representation for UART, may be illustrated as shown on the left here. It will include the transmit and receive channel. Frequently it will be associated with the RS-232 serial communications standard, which defines the frame format and also the physical specifications for this communications channel, but not necessarily. So we might have a serial transmission and serial reception over other serial communication standards. And it will include a data bus which will be able to provide or receive words to a microprocessor, for example. In this presentation we will concentrate on the receiving channel, which comprises three main blocks or three main functions that are referred here on the right. So there will be a baud rate generator, and the receiver itself, and also an interface to provide the word or storage space for these words that are received. Then there will also be some handshaking signals with the external microprocessor or higher level controller. We shall start by looking into the frame format for RS-232 serial communications, and this standard defines that every word that is to be transferred shall start with a start bit that is 0, which will then be followed by a number of data bits. In our case it will be 8, but it isn't necessarily 8 every time. There will be a optional parity bit, and if it exists it may be for even parity or odd parity. Even parity means that the total number of bits, including the data bits and the parity bit, must be even, and the same applies in relation to odd parity. And finally it shall comprise one stop bit, which takes the logic value of 1. Now, after receiving a word, the RS-232 line goes into the idle state, which takes the value of the stop bit. One important thing to mention is that the transmit and receive ends do not share a common clock signal, and as such the baud rate, that is to say the number of bits per second that are to be transmitted, has to be defined in the same value beforehand for both sides, or otherwise it wouldn't work. Now the receiving subsystem, as we have referred before, comprises these three main functions. The baud rate generator produces the sampling ticks that are used to read the input bit stream using an oversampling scheme. Now oversampling is needed because, as we have just said, the receiver and the transmitter ends do not share a common clock. So the best way to ensure that we read the values that are present at the receive line at the appropriate times is to use the so-called oversampling scheme, whereby we will use a number of sampling ticks that will be, for example, 16 times higher in frequency than what corresponds to the duration of each bit to be received at the RX line. This means that whenever a bit period starts, we will wait for 8 sampling ticks, and at that moment we will in principle be in the middle of the duration of this bit, and then we will read at that moment, wait for the remaining 8 sampling ticks in this bit period, and then the bit will change to the following bit in this word. We will again wait for a further 8 sampling ticks, read the new value at the middle of its duration, and so on and so forth. And finally, the third block, as we have also said, provides eventually provides buffering, and it will provide status to the higher level controller or microprocessor. Now, the book makes available all the files for the various listings that are presented. The listing 7.1 corresponds to the VHDL code for the receiver block, and I do very much recommend that you do as I have done here. You import that VHDL description into the project Xilinx project navigator, and then you build a test bench that enables you to use the iSIM simulator to see the operation of this receiver block in practice. In this case, it illustrates the operation of the 16 times oversampling scheme. So the new bit at line RX has just started at this point, and we wait for 1, 2, 3, 4, 5, 6, 7, 8 sampling ticks. At this moment we are at the middle of the bit period. We read the new value here. In this case it will be a 1, so it will be shifted into the deserializer, meaning that the current word, which is now 0, 1 and then all zeros, will at the next bit be 1, 0, 1 and the remaining zeros. So the 1 that was read at this moment has been shifted into the deserializer. Now 8 sampling ticks later, the RX logic value changes to the new bit, and we will again wait for 8 sampling ticks and continue with this process to deserialize the incoming words. The baud rate generator itself needs to produce the sampling ticks with a frequency which in this case is taken to be 16 times higher than the UART's specified baud rate. So if we are going for a 19,200 bits per second baud rate, we will require a sampling scheme that comprises 307,200 sampling ticks per second, and this can be generated in the case of the recommended book, where the board comprises a 50 megahertz clock. Then a modulus 163 counter would be needed. Modulus 163 results from the 50 megahertz clock divided by the number of sampling ticks that were needed to in relation to the 1900 and 200 bits per second baud rate. Now we want to look into how to design a modulus 163 counter, because that has been addressed in the regular sequential circuits section or presentation. That includes actually a modulus M counter that can be used directly for this purpose. you may also check pages 83 and 84 of the book where the VHDL code is presented. Now the receiver block comprises the ASMD chart that is illustrated in this slide. It's simple to analyze this chart. Actually, it comprises only 4 states, and they correspond to the various situations that you see in the RS-232 frame format. So you have the idle condition, the start bit, then the data bits, and finally the stop bit. And that's what corresponds to the 4 states that are shown in this ASMD chart. So it starts with the idle state. Whenever we perceive a start bit, we move on to the start state. We wait for the 8 sampling ticks, then move to the data state where we prepare the UART receiver to sample the various data bits that will be received in the RS line. And then when the pre-specified number of data bits, which in our case will be 8, has been read, we move on to the last state where we read the stop bit, and when that takes place we assert the received on tick output and move over to the beginning at the idle state. We will now look into each of these states with more detail, but notice that actually according to what I have just said, it is the sampling tick signal that drives the transition among the main states that are shown in this ASMD chart. Everything takes place according indeed to whenever these sampling ticks reach a predefined level that enables us to move on to the next state. So we will start with the idle state, and while we are at the idle state, if a 0 is read at the receive line, then we will reset the sampling ticks counter and go into the start state. Otherwise, we will continue indefinitely in the idle state, waiting for a start bit. But as I said, when the start bit has been received, we go into the start state, and we wait for the incoming sampling ticks. Now you must recall that the sampling ticks counter has been reset, so we are in this case going to read the start bit at the middle of its period, so we will wait for 8 sampling ticks. That's why we compare. Whenever a sampling tick is detected, we ask if this is the sampling tick, if the sampling ticks counter is equal to 7, in which case this would be the 8th sampling tick since it started from 0. If it is not, then the sampling ticks counter will be incremented and we continue in the start state. Whenever we reach sampling tick number 8, that is to say when the sampling ticks counter has reached 7, we are at the middle of the start bit duration, and so we can restart the sampling ticks counter and the data bits counter and prepare ourselves to start reading the data bits. So in this case we will have to wait for 15, or actually 16, since we are again starting at 0. We will have to wait for 16 sampling ticks, and these will be the 8 sampling ticks remaining in the start bit period, plus the 8 sampling ticks that will take place in the first half of the data bit duration or period. So whenever 15 sampling ticks have elapsed, we will be in the position where we can read the new data bit value. If this has not yet taken place, then we will increment the sampling ticks counter and continue waiting for further sampling ticks. But as I said, when we are at the middle, having the sampling ticks counter outputs at 15, that is to say when 16 sampling ticks have been received, we will reset the sampling ticks counter and we will include the logic value present at the receive line into the deserializer. And it is this operation here that reads the logic value and inserts it in the deserializer. Then we will check if we have read all the data bits that we expected. If that is not yet the case, we will increment the number of data bits counter and continue in the data state. So if we were working with an 8 data bits word, whenever we have read the data bit number 8, we will be ready to move on to the stop last state. And in this case, what we will do is we will continue to wait for the sampling ticks. In this case, the number of sampling ticks that we shall wait for depends on whether we are working with one stop bit, 1.5 stop bits, or 2 stop bits. So it varies according to what we can choose for this parameter. We will continue to increment the number of sampling ticks, the sampling ticks counter, until we reach the predefined number of required sampling ticks. When that has taken place, we know that we are able to assert the received on tick output and to go back to the beginning, to the idle state. So the VHDL code will now be easy to analyze. We start with an entity declaration that comprises a generic structure for the number of data bits that will be used and the stop bit, the number of stop bit sampling ticks that are required. In this case, 16 means that we will be working with one stop bit. Well, these are the IO pins definition, and then I just call your attention to the beginning of the architecture body, where we create the usual user-defined state type to represent the ASMD chart states, and then the sampling ticks counter and the number of data bits counter. These signals are defined as unsigned because they need to be incremented, and so this is an arithmetic operation that would not be possible if they were standard logic vector type. However, the deserializer itself, which is this last signal, simply uses the concatenate, as you have seen here, the concatenate operator, which is available over the standard logic vector data type, and this will be the data type for the deserializer. Now, the VHDL code for the FSMD state and data registers starts with the very common and well-known state and data registers structure. If reset is 1, then the state register reverts to the initial state, which is idle, and the sampling ticks counter, the number of data bits counter, and the deserializer are all sent into their reset condition. Otherwise, if this is a rising edge of the clock, then the state register will take the value of the next state, and the same will happen with the counters and the deserializer. So this is the standard and very usual structure that you have seen various times before by now. The next state logic and data path functionality in its routing are defined using a process, and I invite you to pay attention to the sensitivity list and to the default assignments that are just those that we expect to find here, namely in terms of the next state, which by default takes the value of the current state. The same happening with the two counters, the sampling ticks and the number of data bits. The same happens with the deserializer, and finally the more output called received on tick is set to 0. And now what we have left in VHDL code for this slide is the representation of the idle state, and it is a very straightforward translation from the ASMD box to the VHDL code. Notice that there is no else statement here, as you may have expect, because since if this is false, then the next state is the current state, and that has been defined here by default, so we don't need the else statement. Now the start state again has a very straightforward correspondence with the corresponding VHDL code, and I just leave as an exercise for you to tell me how many lines of code were saved by the default assignments. For example, we do not need to indicate that the next state will be the start in the case of this decision box holding false, because that has been defined in the default assignments section. Now, please take a moment to see what additional code lines would have to be inserted here if you had not included the default assignments section, and you will be able to answer this question. Now the data ASMD block is probably the one that is slightly more complex, but again it offers a very straightforward correspondence between the ASMD block and the corresponding VHDL code. Actually, the one thing that I think will probably be worth calling your attention to is that the deserializer is implemented using this statement here. So whenever this question holds true, that is to say, if the current value of the sampling ticks counter is 16, then what we shall do is reset the sampling ticks counter. That's what has been said in this assignment, and insert the new incoming bit into the deserializer, and this is done in this assignment. So the logic value that is present at the receiving line takes the place of the most significant bit of the deserializer, and all the remaining bits shift right one position. Well, as for the last state, again, the correspondence between the VHDL code and the ASMD block structure is entirely straightforward, and I invite you to go element by element in this ASMD block and identify what are the VHDL code lines that correspond to them. Well, coming now to the last part, which refers to the interface circuit. So we said earlier that the receiving block has three main functions: the baud rate generator, the receiver itself, and the interface circuit. And this is the third function that we are now looking at. So the interface circuit has two main functions, as indicated here. It should inform that a new word has been read, and it should also prevent that word to be read multiple times. And the second main function is that it may, or it may not, provide buffer space to store words while they wait to be read. Actually, in this case, we are looking at an interface circuit without buffer space. In this case, we are simply using a flip-flop that will be set when the received on tick is asserted, so whenever a new word has been received, and this flip-flop, when its output goes to 1, the receiver empty output goes to 0. That means to say the receiver is no longer empty, it is waiting for words, it is waiting for the microprocessor to come and read the word that has just arrived. Now when that microprocessor reads that word, it will assert the read UART signal, which clears the output, so the receiver empty signal will again go high. Now, because there is no storage space, it may happen that if a new word starts to be received before the microprocessor comes to fetch the one that has just arrived, then we will have what is known as an overrun condition. That is to say, the new word will overwrite the previous one which had not yet been read. Finally, we have a representation here for two slightly more sophisticated interface circuits. In this case, they both offer buffer space. And in this case, there's only one word buffer, so it's a single register that it enables the storage of the word that has just been received. In this case, it is possible that a new word starts to be received before the one that has just been received is read. In this case, overrun will only take place if the second word is completely received before the first word was read. But it is also possible to provide an n-word FIFO, that is to say first in, first out buffer storage space, and in that case we can receive multiple words that will wait in line until the microprocessor or the higher level controller comes to read them. The VHDL codes for these two examples are available in the book, and I recommend that you take some time to go and see how the one-word buffer and how the FIFO buffer architectures for the interface circuit work.